Okay, so this is day 2 of section 4.4. So we're still working with solving exponential and logarithmic equations. Day 1 was solving exponential by creating the same base so that we could set exponents equal to one another. And now we, not able to do that, are going to use our conversion between log and exponential form instead. If you remember that we just had y equals a base of b raised to the x, that can be converted to the log base b of y being equal to the x instead. So since it's the exponent that we're trying to find, then we can just use the calculator to work through that. The log log has the common log base 10, or we could use the natural log, which has a base e. Sometimes we have to because that's the way that the problem is set up. Instead of working through it this way, another way to do it is what's listed on the left from the book, that we also could take the log of both sides and then most likely use that exponent rule that whenever we were condensing or expanding logarithms, that the exponent just moves to the front to solve instead. And then we can, again, not really change a base because the calculator will do it for us, but we can work through that. So the homework was supposed to be page 457. So this is a screenshot of page 457. 24 to 42 even. So again, I'll just do a couple of examples listed here, and then I'll send a PDF of my work with all of them as well to follow along. So for solving each of these, using a decimal approximation, so lots of decimal points, to 2 decimal points, it says, for our answer. So the first couple are using those bases that we're used to. So something like number 24. If we have 10 to the x equals 8.07, then we could, the way that I identified it above, rewrite this as a logarithm. So this is log base 10, which you don't have to write the 10. It's understood to be a 10 because it's the common log of 8.07 is equal to x. That then you can just key in the calculator. You can just type in log 8.07 and you get about 0.091 for your answer. This to me is the easiest way to work through it. You could also use the log rules that were identified above. So we could take the log of both sides. So the log of 10 to the x would be equal to the log of 8.07. Okay, and so then this uses that exponent rule where this x would simply move to the front and become the coefficient. So x would be equal to, or I'm sorry, x times the log of 10 would be equal to the log of 8.07. Now, the log of 10 is a value. It's actually just equal to 1, but just supposing it were some other number, you could divide both sides by the log of 10, and you're going to end up with 0.091 that way. So if you have a preference in solving, you really could do it either way. But again, I think it's just for some of them as easy as using that conversion instead. We don't have to do anything super crazy. So something like number 26, where we have a base of e instead. This time, if I want to convert it to my log form, instead of writing log base e of 0.83 is equal to x, log base e is our natural log. So this really is just the natural log of 0.83 equal to x. So x would be about negative 0.19 for that one. So 0.91, either way I do it, or a negative 0.19. All right, so looking ahead to some of these other ones, and like I said, I will put all of the evens up so you have the examples, so we don't need to do all of them. So let's jump to something like number 32. 32 is 4 e to the 7x, already so much more than what the last one had, equals 10,273. So to solve for this one, I have to get my exponent isolated. I can't do anything with that 4 in front. So if I divide both sides by 4, then e to the 7x is whatever 10,273 divided by 4 is. I left this as a fraction as I was doing my work so that whenever I was solving, I wouldn't have any errors with a decimal point accuracy. It is really easy to end up pretty far away from what we are getting as an answer because we're rounding with all of these decimal points. So I just left it this way. And then again, because it's a base of e, you can write it as log base e of this fraction if you would like, and it is equal to a 7x, or you can just write it as the natural log of 10,273 divided by 4. So the natural log of that value, whatever this is equal to, is some decimal point, and it is equal to 7x. So here's the other difference in our problem. We have to divide both sides by 7. And this, again, is just heavy on the calculator. We just have to key all of these in, and we end up with 1.12. And you can key it in along the way, or you can just wait until the end where you have one nice big fraction to work with. But either way, it's just, like I said, trying to save a little bit of the accuracy with those decimal points. So, last one. Let's look at something like 42. 41 and 42 are quite different than what we had before. And this is the situation where, because we have these exponents, I'm not able to just convert it from the exponential form into a log form. So this is the situation where I need to employ that technique that's listed above, where you take the log of both sides. And again, if you're performing the same operation on both sides, they stay equal. And again, if I pull the exponent to the front as a coefficient, I have 2x plus 1 times the log of 7, whatever decimal point that's equal to. And then I'm going to have an x plus 2 multiplied by the log of 3. So this does get busier, and this one was a little bit harder to save my decimal points. The first thing I did, though, whatever this log of 7 value is equal to, I did in fact divide both sides by the log of 7, so it cancels on the left. And I have 2x plus 1, and then I needed to figure out what this was equal to, because that's going to become the coefficient, and I'm going to have to distribute. And so just the log of 3 divided by the log of 7. Test that out, you should get about 0.56. So I have 0.56 times the quantity x plus 2. And so my next step is to distribute that 0.56x. And I end up with 0.56, distribute the 0.56 to the x plus 2. So I end up with 0.5x plus 1.2. So I have x's on both sides of my equation, constants on both sides of my equation. So I'm going to move my 0.56x to the left side by subtracting it. And then I'm going to move my 1 in a second to the other side also by subtracting it. So 2 minus 0.56x leaves me with 1.44x's plus 1. And that's just equal to 1.12 now on my right-hand side because that canceled out. So if I subtract my 1, 1.44x is equal to 0.12. Divide now by that coefficient to finish my isolation of x. So x is about, and this again with these crazy rounding decimal points and whatever that we have to do. So for everybody that likes decimal points more than I do, we're rounding here, which is not my favorite thing, but it happens. So for this one, obviously this is as hard as it gets. I'm going to finish just by putting some notes off to the side of what we did here. So we have to take the log of both sides. And then here was just a simplify by dividing one of the logs. And we could have gone the other way if we wanted to. We could have divided both sides by the log of 3 instead. And then at this stage, this is old news. This is first semester stuff. So we just had to distribute, and then we wanted to combine our x terms, and then we needed to combine constant term, and then just finish by isolating x and dividing on both sides. So this, again, second way to solve as things get a little bit more involved. I will share all of the evens. If you want to work on the odds for extra practice, send me an email. I'd be happy to share those answers with you as well.